Thanks. So you guys came for penguins and now you've got soil. Yay, awesome. My name's Hadee. I love soils. I study trace elements in soils especially. So trace elements occur in really small amounts in the environment, but they have a disproportionately large effect on the things around them. And one of the things that I love the most about soil science is that it's basically a huge puzzle. It's a puzzle that we've been studying for hundreds of years, and you'd think that we know about most of the components, most of these pieces, what they are and how they fit together. We should be able to make a coherent picture, something that looks like this, but we really can't. This is more of an approximation of our current understanding of soils. So I'm pretty sure there's pieces here that weren't even in the puzzle box. There's like no corner bits. We really have such an incomplete understanding of soils and soil chemistry, and this is why I love it. You can think that you have an issue and you have a solution. You implement your solution and then you have 10 more issues, and you need to go back and you need to look and say, what have we done wrong? What pieces are we missing? And one of the reasons for this is that soils are really diverse. People kind of think of soils as this homogeneous brown stuff beneath our feet, but they vary so much from 1 square metre to another. So these pictures behind me are soils from all around New Zealand. We've got so many different types. We've got sedimentary soils, we've got volcanic soils, we've got sedimentary on top of volcanic soils. We've got soils that have been shaped by land use or climate or rainfall or even vegetation. And New Zealand soils are especially unique. So I didn't make this, I've shamelessly stolen this from a conference that I attended recently. This graph here shows the overlap of different soils around the world, or different soil taxonomy systems, if you're getting technical. And there's a lot of different systems there from different countries, as well as the ones that we use globally. And the more the overlap, basically the more similar the soils. So New Zealand shown in green, and you'll notice that part of that green shape is just so far out on its own. So this just really emphasises how unique our soils are here, how rare they are. And this gives rise to some really spectacular landscapes. So this behind me here, this is an ultramafic boulder field. This is in the Dun Mountain Range. This area is also known as the mineral belt. So we have a lot of sparse tussocky vegetation here. If you look down at the rocks in the soil, it's quite rocky. The rocks are bright green. And this is because the soil is so full of chromium and nickel that it's really shaped this landscape. Not a lot can grow, but it's really stunning. These here are Pākehī soils. So these patches in the middle of the photos where nothing's growing, these occur primarily on the west coast in really high rainfall areas. These areas are so leached, there's no nutrients left in those soils and nothing really grows, but they're a really unique ecosystem. And then we have some really striking volcanic landscapes. So this is Tarawera in the North Island. There is so much iron and so many other minerals in the soil that gives it this bright red colour, and it also makes vegetation difficult to grow here. So we have some really unique landscapes in New Zealand, and they are because of the soils. And I've kind of shown you examples here of how the soils can shape the vegetation. The vegetation can also shape the soils. So these soils here are Kauri egg cup soils. These occur nowhere else in the world. They occur mostly in Northland. These soils here occur only where Kauri trees grow, or once grew. So you'll notice here that there's a big white egg cup-like shape, and then there's a black line under that. So Kauri trees, they grow for thousands of years. They stay in one spot. Their leaf litter is really acidic. So when their leaves fall on the ground and the rain washes the leaves through the soil, washes the nutrients, it also washes this acidity through the soil. And that takes basically everything with it. It strips it until it hits this harder layer, that black line. So you get this really unique shape. That black line kind of mirrors the crown of the Kauri tree. So you can go to Northland where these soils form, you can dig holes, and you can see where these trees once stood. How cool is that? So yeah, like I said, only occur in New Zealand. We have really unique soils, really diverse soils, but we really don't care. We really don't value them that much. We throw around 800,000 tonnes in landfill every year. And this is a really coarse number. Actually, we don't have very good data on this issue, but we know it's an issue. So the soils that I'm talking about here, we call them surplus soils. We refer to them as surplus because we think they're surplus to requirements. So usually when you build a house or a road, any kind of construction, infrastructure project, the soil at the site will be scraped away and it'll be taken to landfill. There's no use for it, so it's treated like waste. A lot of these soils, most of these soils, have nothing wrong with them. We could literally eat out of them, we could grow food out of them, but we don't. They might have concentrations of trace elements which are below background levels, so they're below a pristine environment, but they're not exceeding any kind of threshold in terms of environmental or human health risk. They're perfectly fine, but we throw them away. So just a local example to kind of demonstrate how common this practice is. Te Kaha Stadium, just down the road, right? They went to build this stadium, they went to put the foundations in, they needed to excavate the soil. They didn't have a plan for what they were going to do with that soil on site. So Christchurch City Council put out an ROI for somebody to come and please take away over 10,000 cubic metres of soil. So this is really common. I don't actually know what ended up happening with this. I'd be interested, does anyone know? Probably not. But yeah, just to demonstrate, very common practice. So obviously this seems super unsustainable. Soils are a really finite resource. They take thousands of years to form. They're not renewable in any kind of meaningful time frame to us. Once they're eroded or contaminated or gone, we can't really get them back. There's high disposal costs as well to throw them away. I'm pretty sure the gate fee at Burwood landfill was $110 a tonne. So actually for CCC to dump all that soil would have cost over $1 million. Probably one of the reasons they asked for people to come and take it. And it generates emissions, obviously trucking these soils around the country to landfill sites. So why do we do this? Well, I mentioned that we don't have a lot of data on this issue. We don't have a lot of data on how much is disposed of, where it comes from, where it goes, what it contains. And this is kind of underpinned by the fact that there's a lack of agreement on what we should be measuring and who should be measuring it, because it costs to measure these things. So who's going to do that? And there's a couple of regulations as well that have come into effect here that have kind of unwittingly led to the generation of surplus soils. So I'm going to paraphrase for brevity and your sanity. One piece of regulation in particular, the NESCS, or the National Environmental Standards for Managing Soil Contaminants and Human Health. How many times have I said that quickly? Quite a few. A really good piece of legislation. We should probably have national environmental standards, and we should probably protect human health. There was a clause in the NECS which was interpreted to mean that any soils that are disturbed that have concentrations of trace elements above background need to be disposed of in a landfill. So this graph here, this shows the proportion of different waste types that are disposed of in landfills in New Zealand, in Class 1 landfills. That dark blue area at the top, that's inert material. So that's mostly soil, everything in that area there. The NESCS was introduced in 2011. This red line here shows 2012. So you can see that post the NESCS, there was a huge increase in the amount of soils that are thrown away in landfills. Soil now makes up, inert material now makes up over half of what we throw away in Class 1 landfills in New Zealand. So it's such a shame. We really should be reusing this really valuable resource. So I guess where can we start? One of the things that we can do is we can raise awareness around the use case for soil. How can it be used? How can it lead to benefits? We can use it in so many applications. We can use it for landscaping, for horticulture, for urban agriculture. I mentioned before that New Zealand soils are really unique and really specific, and some of them, we have huge areas in the North Island of pumice soils. Now, pumice soils have a really high water holding capacity. They can hold so much more water than a lot of other soils. We can use these for stormwater mitigation. We can use these in areas where we need to mitigate a lot of rainfall. We've got increased rainfall due to climate change. Our cities are flooding. These soils could possibly help us if we put them in the right places. We also have soils called allophanic soils. So these are found also mostly in the North Island. These soils can hold up to 18% carbon. I think on average about 10% carbon. That's like more carbon than any other mineral soil. Around the world, the average is like 2%, so that's quite a lot. We can use these to sequester carbon. We can use these soils to replace eroded soil. We can use it for habitat restoration. There's so many use cases. But I think what we need to do first, and I'm sorry, this is a cheesy slide, we really need to value soils. We need to value urban soils. And I put the emphasis on urban here because even amongst soil scientists, urban soils are kind of disregarded. They really don't get the credit that they deserve. Some people don't even consider them as soils. Most of our soil maps don't even include cities because people think they're just contaminated or they're compacted, you know, what's the use of that soil? But it really is valuable and it deserves credit. So thanks for giving me captive audience for that. I'm going to talk a little bit about trace elements. So my pet passion here, my second pet passion, the reason that I love trace elements is because you could look across a landscape and you'd be really hard pressed to find a process that's not affected by them. So when I'm talking about trace elements, as I mentioned, we have essential trace elements, things like iron and zinc and copper and selenium. We need these. Plants need these. Plants don't need selenium. They need some of these. Microbes also need these. We need them in the right quantities as well. And then we have other elements that are non-essential, things like lead and arsenic and cadmium. Now, if we have too many of these, that can cause issues for the environment and for us. So, two sides of a coin here. But trace elements are really important for so many things. I'll just talk about a few. The first is food quality and nutrition. So, over the past 50 years, our key crops, our staple crops, have been declining in their nutrient density. We now have much less nutritious food than we did 50 years ago. Around the world, most of our wheat doesn't meet the dietary requirement for zinc. So why? We've been breeding for higher yielding varieties. So we now feed more people, but we're feeding them less nutritious food. These crops are great because they've allowed us to feed the world, but they don't take up the nutrients that they once did. So we have a lack of nutrition in our food. Conversely, if you have too many potentially toxic elements in your soil, such as cadmium, and your food takes up a lot of that, that can cause problems. So they can affect through food chains, they can affect our physical health and also our mental health. There's so much research that's coming out recently on the essentiality of these essential trace elements to not just our physical health, but our mental health and our cognitive functioning. They can affect water quality. So aquatic organisms are particularly sensitive to copper and zinc. And after the earthquake rebuilds, there was this great idea that every building was going to have a copper roof. That was really awesome until people realised what it was potentially doing. So every time it rained, this rainfall was carrying copper off copper roofs into our waterways, where that was having a potentially detrimental effect on our aquatic life. They're really important for nutrient cycling, particularly nitrogen cycling in our agricultural system. So all of the food that New Zealand produces, we need trace elements in the soil for this. They're really important for greenhouse gas emissions. So copper, selenium, molybdenum, all of these elements in soils are essential for the manufacture of enzymes that can mitigate greenhouse gas emissions from our soils. If we don't have them there, our emissions peak, they rise. And also contaminant toxicity and degradation. So a long time ago, we had this awesome thing called DDT. We thought it was a really good idea to put it all over our soils because it could kill grass scrub. Turns out, no, not a good idea. We've realised that, and it's okay because DDT degrades over time. It basically deteriorates into nothing. Also, we thought, it actually turns out that my PhD co-supervisor, Sally Gore, she conducted some research that found that in the presence of copper, DDT doesn't degrade like that. And so you have soils where you have legacy DDT residues that actually haven't degraded because there's copper there as well. So that assumption doesn't hold. And that's kind of what I mean about soil science being a puzzle and us just not having all the pieces yet. So my research is basically focused on finding the sweet spot when it comes to trace elements. We need the right amounts and we need the right chemical species of them as well, because they can exist in different chemical forms. So I guess this plot here shows it's like the toxicity deficiency curve, right, of an essential element. If you don't have enough, you get sick. If you have the right amount, that's great. If you have too much, again, you get sick. This becomes complicated because humans need different trace elements to plants. We need different amounts than other animals do. Microbes also need trace elements, so we need them in the right forms for basically everything. And this gets further complicated by the fact that trace elements interact with other trace elements, so I don't really expect you to be able to make this out, but this is an interaction matrix. So down the side and along the top, you have different trace elements, and anywhere that they meet and the square's coloured, it means that they interact. So they can interact in a heap of different ways. They can be antagonistic. So you can have cadmium and zinc in your soils, and your plants probably won't take up as much cadmium if there's more zinc, which is good because we don't want cadmium in our food. But if we have copper and iron together, your plants will actually take up more of both. So they have this synergistic effect, this additive effect. There's some squares here that just say antagonistic and /or synergistic, as in, like maybe they do one of the things. Maybe it depends on what concentrations they're in or what forms they're in or where you are. And then there's one that just says possibly antagonistic, as in, again, like we don't really know. We don't have all the parts to the puzzle. One of the things that we can do to kind of help us disentangle this really complicated process is we can use models, environmental models. So a lot of environmental processes can basically be reduced down to a set of mathematical equations. Not well, but like they can. So we can build these models. I developed one during my PhD. I affectionately call it Steve. Steve stands for the Soil Trace Element Visualization and Evaluation Model. I love Steve. Steve's great. Steve basically tells me if I have a piece of land and I put some fertilizers on it now and then it rains this much per year and I leave it for 20 years, what will happen in 100 years? Where will that trace element in that fertilizer end up? Will it be in the plants? Will it stay in the soil? Will it be in the groundwater? So just an example of the kind of things that we can use, the kind of tools to kind of disentangle this really complicated process that we try to understand. I've got a couple of minutes left, so I'm going to leave you guys with like a good news story, because I feel like a lot of environmental science can be kind of depressing. So I want to share a nice story, and it's not strictly related to my research, but I did encounter it during my research, so it counts. So this shows the parkgrass experiment. This experiment is located in Rothamsted Research in the UK. It's been running for almost 200 years, and it was designed to test the effects of different management regimes on the production of grass. Different fertilizers, herbicides, management, tilling, all that kind of thing. It's evolved a lot since it was established. It's now considered an ecological experiment rather than one focused on agriculture. And it's the world's longest running ecological experiment. And there's plots in this field trial that have had no herbicides applied for almost 200 years. They don't have any grass in them anymore. They basically just contain weeds and wildflowers. So this is one of the wildflowers found in this experiment. This is a locally rare and declining species. This is a bee orchid. This now grows all over the Rothamsted campus. This little thing has evolved over millions of years to not just look, but to smell like a female longhorn bee. And now it's growing everywhere. So I have no idea what a bee smells like. Please don't ask me, but I'm more than happy to answer any other questions. Thanks.
Hey, first of all, thank you so much. What a wonderful speech. I wanted to ask if you could give, I guess, a bit of a basic run-through of the nitrogen cycle and what that means and why that's important for the recycle of the trace elements you're talking about.
Oh, you've asked the wrong person. No, so the nitrogen cycle, I don't focus on macronutrients, I'll be quite honest. the bit of work that I do that relates to the nitrogen cycle focuses on how trace elements can impact those. So when we apply nitrogen to land, there's two processes. Basically, there's nitrification and there's denitrification. Those processes can result in like nitrates, which are, you know, the big baddie chemicals that you hear about getting into our groundwater. If you have like a full denitrification cycle, basically you go the other way and I'm not explaining this very well, I don't really know this that much, but you basically end up with nitrous oxide, and if you get to full denitrification, you end up with inert nitrogen gas, which goes into the atmosphere. So, yeah, I'm sorry, you should ask somebody else that.
Thank you. The soil, the increase in soil going to landfill coinciding with the rule about higher than regular trace elements, like that, can we say that's probably contaminated soil? And if so, what would be better things to do with it given it's contaminated?
Well, that's interesting because it's a bit of a terminology kind of discussion there. So you could consider anything that has any kind of input into it is contaminated. But I think the really important question here is, does that soil pose a risk? Is there any reason that we can't reuse it? So, like, most of the soils in your back garden would be considered contaminated if you go by that definition. You'd be really hard pressed actually to find soils that weren't. Even like native forest soils, you know, there'll be something that's come in from somewhere. So if you're going by that definition, it's not a very good one to use in my opinion. I think we should be looking at, do these soils exceed any risk-based thresholds? If they do, then yes, sure, we should probably not be growing food in them. We should put them somewhere where they're not going to hurt people or the environment. But if we're just talking about kind of lightly contaminated soils that actually pose no risk, I don't see any reason why we couldn't use them for any of the reasons that I mentioned. Yeah.
Just similarly on that, is there anywhere in the world where they are doing better with surplus soil than we are here?
Yes, there are. So I recently had the privilege of presenting work on this at a conference, and I basically said, does anyone else work on this around the world, and can you come and talk to me? So in France, there's a company that's taking these soils and they're manufacturing them into what they call like technosols, which are basically like human-made soils, and they're selling them for specific purposes. I think there's similar work going on in New York, where they're looking to see how they can reuse their soils as well. And I'm super happy to say that there are initiatives, like we're starting to look at this in New Zealand. There is movement in this space, so yeah, I hope that we can follow suit.
Thank you so much. I wanted to ask about those initiatives that are currently being implemented or under research so that something can be done.
In New Zealand, you mean? Yeah, there is a lot of movement in this space. There's Wastemins, Waste Minimisation New Zealand. They are doing a lot of work in this space, looking at how it can be reused. We wrote a report, basically, which was cited by the Parliamentary Commissioner for the Environment. So they recognised that there was a need for something to be done here. It's also a big thing in the contaminated land industry. So like private sector is really looking at this, because potentially there's a lot of money to be made. So there are, like, more and more I talk to people, I talk to consultants and private sector workers, and they all say they're really interested in this. I know personally of some of them that are starting to try and fund some initiatives. I can't tell you exactly what they are, I'm sorry, but yeah.
Is there any way that soil can heal itself?
Yes, if you give it long enough. That's the thing when I said like it's a finite resource on any timescale meaningful to us. You know, it depends what the issue is. I mean, there's so many issues that could arise. Sometimes soil, if you kind of just leave it for long enough, like it will rehabilitate itself. Sometimes it's harder to repair the damage. It really depends, yeah, what issue you're talking about.
Any other questions? Great. Let's give Hadee another round of applause.
Thanks.